Hello, my name is Ibar. I present to you multi-level graph label propagation for image segmentation. That is part of my doctoral study. This is the outline of the presentation. First, I will talk about introduction, then the contribution, then the related work, then the proposal, then the result, and finally the conclusion. In this work is about the problem of automatic image segmentation. In some times, for humans, it's very confusing to determine what is a best segmentation. It can be subjective from different people's perspective. In this context, for computer, the complexity of the automatic image segmentation problem increases more. In graph-based segmentation methods, a graph is first constructed to represent the image, where the vertices are pixels and the edges are the weight between vertices. Then segmentation is obtained using graph clustering algorithms. The large number of vertices and edges of the graph's representation is a motivation to propose new methods faster and more accurate. Graph clustering algorithms were used directly for automatic image segmentation. In this context, in some cases, information from the image domain has been omitted. Algorithms such as fast-greedy, Lováin, and label propagation have a stochastic result. This does not allow the reproduction of segmentation results. Fast-greedy and Lováin are of multi-level nature, but label propagation is not. The multi-level strategy is useful for handling large graphs. The main contributions of our work are a multi-level strategy to create graphs that represent images in order to simplify the propagation of labels. Introduction of two deterministic traversal strategies to propagate labels suitable for image context. Propose a fast iterative multi-level method for color image segmentation based on label propagation. The fast-greedy method is of multi-level nature, and it was applied directly to image segmentation. The Lováin method is of multi-level nature too, and it was applied directly to image segmentation. The label propagation method is not of multi-level nature, and it was applied directly to image segmentation. In this context, we propose the multi-level graph label propagation method. The method uses information of the specific domain of image. Given a color image, our method starts to pre-segment the image with superpixels. Then, to describe the superpixel content, features are extracted for each superpixel. In multi-level form, the label propagation is performed. The final result of the segmentation is obtained at the last level of propagation. Next, I will detail each step of our proposal. reduce the number of vertex of the graph in this step, superpixel presegmentation is performed. The first parameter of our method is the size length of the square superpixel denoted by letter S. To compute the number of superpixels, we use this equation where n is the number of pixels. To describe the content of superpixel, in this step are extracted features for each superpixel. To do this, we first convert the color into the Scilab color space. Then we computed the three first statistic moments of color per channel. For each superpixel, the out is a vector of feature of 9 dimensions. In an iterative form, in this step, a multi-level label propagation is performed. In each level, 4 tasks are executed. First, a graph is created. Then, the label propagation are executed using two deterministic traversal strategies. In function of the label propagation result, superpixel and feature are recomputed. The superpixels with the same label are merged. For each new superpixel, features are computed by calculate the mean of each feature. These new superpixels and new features are used as input for the next level. In the graph construction, the vertex are represented by superpixels, and the edges are created with the first neighbor of each superpixel. The edges are created using a Gaussian similarity function and are delimited by a threshold parameter denoted by letter T. This is the second parameter of our method. In the first picture, we can see an example of the classical random traversal strategy using in complex network. In the second picture, we can see an example of the convolution traversal strategy. In the third picture, we can see an example of the spiral traversal strategy. In compare with the random traversal, our traversal strategies use the localization of superpixel on the image. Here we can see an example for update the label of one vertex. For each iteration, the label of each vertex is updated with a height frequency among the labels of the neighbor for each vertex. In the next iteration of the multi-label propagation, the following tasks are repeated: graph building, label propagation, rebuild superpixel, and rebuild fixtures. The iteration of the multi-label propagation ends when the number of the labels don't have a change in the reduction in relation with the previous level. This is interpreted as the convergence of the algorithm. The segmentation is obtained at the last level, where regions are constructed by pixels with the same label. We use the Berkeley dataset in test version to assignment of parameters, and we use Berkeley datasets in validation version to compare with related work. To measure the quality of the result, we use three types of metrics: covering, contour-based, and probabilistic rand index. All metrics measure similarity between ground truth segmentation and segmentation produced by some methods. The goal of this experiment was find the best values for the two parameters, that are side length of superpixel denoted by letter S and thresholds denoted by letter T. In the picture, in x-axis, we can see the variability of the size length of superpixel, and the y-axis we can see the accuracy values of segmentation. The color lines denote variability for thresholds parameters. For the convolution traversal strategy, we have best result for side length of superpixels in this range, and we have best result for thresholds in this range too. In the same way, for spiral traversal strategy, we have similar result that convolution strategy. The best value of the parameters S and T are equal of convolutional traversal strategy. From left to right, we can see two examples of result for a spiral strategy. In first column, we can see the ground truth manual segmentation. From second column to the sixth column, we can see the evolution of the first 5 iterative multi-level segmentation. Here we can see the quantitative results, where we compare our method with other related methods. We observe best result for our method. Specifically, the spiral traversal have more accurate result. Here we can see the qualitative result. First row present the ground truth segmentation. Second row present the result using the fast greedy method. Third row present the result using the Lobine method. The last row present the result of our method with a spiral strategy. In this work, we present MGLP, a fast and accurate multi-level method for automatic image segmentation based on a reformulation of the label propagation method originally used to identify communities in complex networks. Our method incorporates two deterministic propagation strategies that take into account information from the image domain. Several experiments carried out with the Berkeley dataset have shown that proposed method is faster and more accurate when compared with similar graph-based methods. These are the main references used for this presentation. Thank you for your attention.